In the last two sections of this chapter, we'll be solving equations with trig functions. So something that we want to keep in mind is whenever we have a solution, just check your answer to make sure that they work. So you could get an answer, say, like pi over 2, and maybe your initial equation had tangent in it. Well, tangent is undefined at pi over 2, so that solution wouldn't work. So just make sure that the solutions you get make the original functions defined. The strategy when you solve these trig equations to, if possible, write with only one trig function. And that will make things much easier. It's like when you have an equation, you always want to solve an equation with just one variable, not many variables. So let's go ahead and look at what happens if we have an equation with a trig function and we just have one trig function. Well, in this case, we would solve it like we do any algebraic equation. We would try to get the sine of x, that function by itself, on one side of the equal sign. So I'm just going to go ahead and minus 1 and divide by 2, and then I'll get sine is equal to negative 1 over 2, or sine, of x. Sine of x is equal to negative 1/2. So we have to think of when is sine equal to negative 1/2, because we're supposed to be solving for x in our interval from 0 to 2 pi, not sine of x. So if you go ahead and you look on your unit circle, this is a negative value, so we know it's going to be in quadrants 3 and 4 for sine. And negative 1/2, that would be at 7 pi over 6, and at 11 pi over 6. So those would be the two solutions within this interval from 0 to 2 pi. Now typically you will see these written as the solution set, 7 pi over 6, comma 11 pi over 6. So that's it. If you have one trig function, just use algebra properties to get that trig function by itself. And then to solve for the argument, in this case the argument is x, you would just go to your unit circle. Now just pay attention to what interval you're giving to solve. Like for instance, if I was given the interval from negative 2 pi to positive 2 pi, then I would have had two more solutions. Another thing we do in algebra when we can't directly solve is we try factoring. Now remember, whenever you want to solve an equation by factoring, the goal is to set it equal to 0 first and then factor it. So the idea is if you have a product equal to 0, then you could break it down into smaller pieces. For example, in example 2, we have, and pay attention, this is degrees now, from 0 to 360 degrees. We have the equation 2 sine of x cosine of x equal to sine of x. Now you may be tempted to divide both sides by sine of x, but you can't do that because we don't know if sine of x is equal to 0 or not. And we're not allowed to divide by 0. Plus, if you get rid of that sine of x function, you might be losing a solution. So the goal here, since it is two trig functions, and it doesn't seem feasible for me to say replace cosine with an expression that just has sine, because when you think about it, cosine would be equal to plus or minus the square root of 1 minus sine squared of x. That's complicated. So in this case, I'm going to try factoring because that seems a little bit simpler. Set it equal to 0 by subtracting sine of x from both sides to get 2 sine x cosine x minus sine of x equal to 0. Now you might have noticed in the beginning that that 2 sine x cosine x is going to be equal to sine of 2x by one of our identities. But then what you'll have is sine of 2x equal to sine of x, and you have the arguments different. One is a 2x, one is an x, and that would actually be very difficult to solve as well. You want to make sure the trig functions are all the same and their arguments are all the same. So in this case, I could factor out the sine of x, and I would have 2 cosine of x minus 1. And then I have a sine of x. So what I've done is I've broken this down into two factors. So I have this product set equal to 0. And in each one of those parentheses, I have a single trig function, which was my goal. And now I can simply set sine of x equal to 0 and 2 cosine of x minus 1 equal to 0 and solve these equations separately. So again, this is just a strategy that we had from algebra. So now the sine of x equal to 0, sine is equal to 0 at 0 degrees. So remember, we're working in degrees. So this would be at 0 degrees, but also at pi or 180 degrees. And within this interval from 0 to 360 degrees, there's no other solutions. This other equation, if I were to add 1 and divide by 2, I would get cosine of x equal to positive 1/2. So cosine is positive 1/2 in quadrants 1 and quadrants 4. In quadrant 1, it corresponds to pi over 3, which is 60 degrees. And in quadrant 4, that would be 300 degrees. So again, we usually write this in set notation. Notice I did not write my solutions from smallest to largest. Remember, when you're putting elements in a set, order doesn't really matter. However, in your textbook, they will have solutions from small to large, but it's not necessary. Let's try another one. Okay, in example 3, we're solving, and our interval is in radians from 0 to 2 pi, so our answer should be in radians. When I look at this equation, it's only sine, which is good. But it's a sine squared minus 2 sine of x plus 1 equal to 0. So it's already said equal to 0. The idea is, can I factor that? Because of the sine squared, I can't simply get sine equal to something, some number. So it kind of looks like a quadratic equation, and I'm thinking maybe it'll factor like a quadratic equation, but it's kind of hard for me to see because the function sine of x is a bit distracting. I'm going to do a temporary substitution, and I'm going to let y, so I'm going to pick a variable different than x because x is already being used, equals sine of x. And that will allow me to rewrite this equation as y squared minus 2y plus 1 equal to 0. And then maybe it's easier for me to see if it factors or not. In this case, this does factor. It's y minus 1, y minus 1. So each of these factors is the same. So I just get the one solution, y minus 1 equal to 0. So now that it's completely factored, I'm going to go ahead and substitute back for the sine of x. So it's sine of x minus 1 equal to 0, or sine of x equal to 1. So sine is equal to a positive 1 at only pi over 2 within this interval. So remember, our interval that we're working with is 0 to 2 pi. So the solution set is just pi over 2. Now sometimes, such as in example 4, you will recognize it as being quadratic, but maybe it doesn't factor. But there still might be a solution. So in this case, we would try to use the quadratic formula and see what happens. This says solve over the interval from 0 to 2 pi. Notice it doesn't say do not use a calculator, so that's sort of a hint that we'll probably have to use a calculator. Now again, I just have tangent, which is good. And it looks like quadratic because I have a tangent squared. So maybe I will try factoring again. The tangent of x is distracting, so I'm going to do a substitution. And again, I'm going to use y because x is already in use, but you could choose whatever variable you want, as long as you don't choose x. When I look at this equation, it's y squared minus 3y plus 1 equal to 0. And unfortunately, this does not factor. So since it doesn't factor, I'm going to try using the quadratic formula. In this case, a is equal to 1, b is equal to negative 3, and c is equal to positive 1. So our solution will be y equal to negative b, so negative 3 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. If we simplify this, we get y equal to 3 plus or minus the square root of 9 minus 4 is 5, all over 2. At this point, I don't recognize that value. So remember, y was equal to tangent. So what this says is tangent of x is equal to, I'm going to break this up as 3 plus the square root of 5 over 2. And tangent of x is equal to 3 minus the square root of 5 over 2. And I don't recognize 3 plus square root of 5 over 2 or 3 minus square root of 5 over 2 on my unit circle. So that's not a value that we know, which is why in this case, we have to use a calculator to solve. And we have to use our tangent inverse to get the x by itself. So here again, we're going to use a calculator. And we're going to solve x equal to tangent inverse of 3 plus the square root of 5 over 2, x equal to tangent inverse of 3 minus the square root of 5 over 2. Now, I don't know if 3 minus the square root of 5 over 2 is negative or positive, but I know that 3 plus square root of 5 over 2 is positive. So in my first possible solution for x, I have a positive value for tangent, which means I'm going to get 2 solutions. Now remember, our interval is from 0 to 2 pi. So I'm going to have 2 solutions, one in quadrant 1 and one in quadrant 3. If I put this in my calculator exactly as I see it, that's fine. If you did want to have a decimal approximation for 3 plus the square root of 5 over 2, if you wanted to do that first, that's okay, but don't round it. If you're going to do that, make sure that you put everything that you see on your calculator, and I have 2.6180333989. So now that I've approximated that value of 3 plus square root of 5 over 2, I can see that it is positive. So I'm going to have these 2 answers, one in quadrant 1, one in quadrant 2. When I look at the 3 minus square root of 5 over 2, that's also going to be positive. It's a small number, but it's still positive. It's 0.3819660113. So for that particular value of x, I'm going to have 2 solutions as well, one in quadrant 1 and one in quadrant 3. When I put this in a calculator, I get x is approximately equal to 1.2059 32499. Okay, so remember, we were supposed to get 2 solutions, but whenever you use your calculator with the tangent inverse key, you're only going to get 1 solution. And in this case, our solution will be in quadrant 1. If you were to look at those radian measures as approximations in your calculator, you would have 0. Pi over 2 is approximately equal to 1.57. So you could see that 1.2, and I'll just write 1.2, it's an approximation, is in quadrant 1. So think about tangent. If you have this other solution in quadrant 3, you're going to use the period of tangent, which is pi, and you're going to add pi to the 1.2059 solution. And if you add pi to that, you will get the value in quadrant 3. Let me go ahead and fill out the approximations on my unit circle. So at pi, we have 3.14, and then 4.71, coming all the way around 6.28. So I just want to verify that when and here I'm going to just box this first solution. When I add pi to that solution, and I'm not going to approximate pi, I'll put in the exact value. Do I get something in quadrant 3? 32499. And I get 4.34 in my calculator, which is in quadrant 3. So that seems reasonable. And then 7, 5, I'm going to put the whole thing down. 25152. If this is a homework assignment and they say to round the answer to the nearest thousands or maybe one decimal place or whatever they ask you to round it to, remember you're rounding this final answer. You're not rounding the value that you're putting into your calculator. You're rounding the value, the final answer that you get out from your calculator. So we have two solutions for that first x value. Now when I look at this second, again, positive, 0.38, going to have a value in quadrant 1, quadrant 2. Let's look back at that unit circle. I'll use a different color. So 0.38, that's a very small value. So it's about 0.4. If I add pi to that, I should get a value in the 3s in quadrant 3. And that seems reasonable. Think about adding 3.14 to 0.38. We should get that value in quadrant 3. So again, very careful whenever you use the inverse key in your calculator. It's just going to give you one answer, but you may have more given the interval that you're supposed to find your solutions on. In this case, I get x is approximately in my calculator, it's a small value, 0.36486, 38282. If we add pi to this, so I'm just going to add pi, then I get my second solution, which is approximately equal to 3.506 456 482. And yes, that is in quadrant 3 as expected, and it is close to pi, 3.14. Now, that's probably the worst type of problem because, I mean, it's totally understandable, but it's a really long problem. Now, sometimes it's helpful if we use identities to solve. In example 5, it says solve over the interval 0 to 2 pi, but don't use a calculator. And that's actually good news. Whenever you see don't use a calculator, that tells you, oh, the answers are probably going to be nice, not like our prior example. So here I have a sine and a cosine. If possible, I want to write this as one trig function. So what I'm going to do is I'm going to use that Pythagorean identity that says sine squared plus cosine squared is equal to 1. So now if I solve for the sine squared, I would have 1 minus cosine squared, and I can replace sine squared. If I solve for cosine squared, I'll have 1 minus sine squared, and I can replace the cosine squared, which would be a little bit harder because it has a negative in front of it or a minus. So you do have to remember to distribute the negative. So I'm actually going to use that one, that harder one. And I'm going to solve this for cosine. Oops. If I can write. I'm going to call this, solve this for cosine squared and get 1 minus sine squared. So I'm replacing the cosine squared x with 1 minus sine squared. In this equation, it's going to be sine squared x minus, and here is where you have to have your parentheses, 1 minus sine squared x, quantity equal to 0, so that you don't forget to distribute that negative. This will give me sine squared x minus 1 plus sine squared x. So not only do I have this written in terms of one trig function, I can actually combine these like terms. I have 1 sine squared plus 1 sine squared will give me 2 of these sine squared x's. So add 1, divide by 2 to get the sine squared by itself. And now I need to solve for sine, square root both sides, but don't forget the plus minus. It's going to be plus or minus, oh, there goes my voice, square root of 1 over 2. So that's simply 1 over the square root of 2, but then we have to rationalize. So notice we have sine of x equal to plus or minus the square root of 2 over 2. And that's a value that we know. I'm going to again just look at our unit circle. And think about these two values. We have sine of x equal to the positive square root 2 over 2. So that would be quadrant 1, quadrant 2. Sine of x equal to the negative square root 2 over 2. Oops, sorry. So that would be quadrants 3 and 4. In quadrant 1, it's pi over 4. In quadrant 2, it's 3 pi over 4. So for the negative square root 2 over 2, that would be quadrant 3, 5 pi over 4. And quadrant 4, 7 pi over 4. So those are all the solutions within the given interval from 0 to 2 pi. Again, I would write that as a solution set and list them all. I think the thing to remember here is to be conscious that you're not just going to have one solution oftentimes. Sometimes you will. You may have many. And in fact, in the next section, we're going to look at what happens when we have infinitely many solutions. Something to keep in mind is as we solve equations, it is possible for us to have no solution. So I have sine squared minus cosine squared minus 3 equal to 0. Two trig functions. This time I think I'm going to replace the sine squared with 1 minus cosine squared. Again, I'm just using that Pythagorean identity. Sine squared plus cosine squared equal to 1. So notice that if I were to solve, I get sine squared is equal to 1 minus cosine squared of x. So 1 minus cosine squared x minus cosine, oops, why do I keep doing that? Minus cosine squared x minus 3 equal to 0. So I have a minus cosine squared, I got 2 of those. And I also have a 1 minus 3, so I'm just combining like terms. So this would be a minus 2. Now if I get the cosine squared x by itself, by first adding 2 to both sides and then dividing by a negative 2, then I get cosine squared is equal to negative 1. So this is something squared equal to a negative number. That can't happen. So right now I see that there's no solution. Well, let's just say that you didn't recognize it. You're working on autopilot. You square root both sides to get cosine of x equal to plus or minus the square root of negative 1. Well, square root of negative 1, that's the imaginary number I. It doesn't exist. So in this case, we have no solution. And it would be written in set notation as that 0 with a slash through it. So remember that means no solution as well. So other cases where you may have no solution is the one I mentioned in the beginning. If you had an equation, say, with tangent, and you ended up with pi over 2 as the solution. Well, tangent's undefined at pi over 2. Or say you had cosine of x equal to 3. Cosine's never equal to a number greater than 1, so that would be an example where there's no solution as well. So that's it for this section.